optimization problems, and this next optimization problem is an optimization problem from grade 12. So the area and the parabola questions, you were first introduced to those optimization problems in grade 11, where you had to find a vertex. Here is one that you would have done in grade 12. So a rectangular sheet of cardboard measures 10 centimeters by 7 centimeters. And squares are cut out of the corners so that if you fold it up, if you fold it along these green lines, it would make an open-ended box, which you could draw like this. Where I made the bottom the green lines. So what we do in a question like this is we say, well, we don't know how big those squares are that we're going to cut out, so we're going to introduce a variable and say that those squares are x, which would make this side now 10 minus 2 of those squares, and this side 7 minus 2 of those squares, and the height x. So we could have a volume of this by multiplying length times width times height. And if we wanted to, we could, right, if I was going to take the derivative of this right now, I'd have a product rule inside of a product rule. So this might be one that we decide I'm going to multiply this out. And get the following equation. Now, if this was, it says at the end, calculator. If this was a calculator question on a test and you were trying to find the maximum, if you had a graphing calculator, then for sure, you would use its powers to draw the graph, find the maximum. That's a lot easier than doing all the work, right? If this was a calculator question and you were doing this in university, they would probably say you're allowed a calculator, but not a graphing calculator. So now your calculator can only help you with calculations. You might still need to do the calculus around it. Okay? So we are trying to find the maximum volume. Well, again, in grade 12 pre-calculus, the best you could have done was graph this on a graphing calculator and find it. In grade 12 pre-calculus, you would have known the following. Since this is in factored form, can you see, and I'll write them underneath, that these are your x-intercepts. X equals 3.5, x equals 5, and x equals 0. And in grade 12 pre-calculus, you would have said, okay, if I know my x-intercepts are at 0, 3.5, and 5, and I know that this will make an x cubed graph, and an x cubed graph starts down there and ends up there. From grade 12 pre-calculus, you would have had this general shape known. And what we have in this general shape, where this is x and this is volume, what we have from this general shape is we know that there is going to be a maximum there. We also know from this general shape, if we think about the situation, that technically this yellow part is the only part of the graph that makes sense. We can't have a negative volume. They'll be like, here's a box with a negative volume. Look, put something. It's like a little black hole, right? Oh man, that would be like the newest terrorist invention. ship black holes in the mail. The person opens it up, gets sucked in. Where did they go? No one knows. So, yeah. So this is the only part that makes sense. You can't have negative, oh, but you're like, well, it's positive here again, but if you cut out a size of square bigger than 5, you wouldn't have any cardboard left. That also doesn't make sense. In fact, anything bigger than 3.5 would completely get rid of the 7 centimeter side. So it's nice to have the grade 12 pre-calculus to give us a quick sketch, but the grade 12 pre-calculus doesn't find this maximum for us. Now that we have calculus, I can easily take the derivative of this, especially since I multiplied it out. And this is most likely where the calculator part would come in university. Because if you had this equation, you set it equal to 0, you might notice you could factor out a 2. And in your university professors, some will factor out the 2, and some will just say, let's divide by 2. Since 2 is just a number and not a variable, it does the same thing. If you're factoring out an x, you would want to do that instead of dividing, because then you'll have still solutions. But you'll often see in university they'll say, well, we can divide everything by 2. That at least makes this a nicer number. Okay? Now solving this, you'd either have to factor or use the quadratic formula. And at this point, looking at the numbers, since the numbers are bigger, as soon as numbers get bigger, factoring becomes more difficult. This would probably be a place where I would say, hey, we should use our quadratic formula. I'll write it out here for you again. And solve for this way. So we're going to get x equals 34 plus or minus 34 squared minus 4 times a 6. And even these numbers seem to make us want to use our calculator. Simplified, this is 34 plus or minus the square root of 316 over 12. The two answers that this gives are 4.31 and 1.35. Okay? So a couple of things. Using my grade 12 graph, I can tell that's not the answer, because that 4.3 is bigger than the 3.5, cutting away too much cardboard, or even just knowing that 4.3 would cut away too much, the answer has to be the 1.35. And I use my grade 12 pre-calculus sketch, I know that that's a maximum from that. I could still make my number line, right? It wouldn't have been wrong to do 1.35 and 4.31 and know that my graph goes increasing, and decreasing, then increasing again. I could plug those values into my derivative to find that. And that would also tell me that the 1.35 is the maximum from there as well. Reread the question, because did it say to actually find the maximum volume? Yes. So now I would go to my calculator, I'd take that 1.35, I'd have to plug that into my original equation in my calculator. So rounded to 3 decimal places, I got 42.377. Right, so I'm allowing you to use graphing calculators on your exam. And if you don't have one, you can borrow one. So if you were able to type that in, y equals right, there's that maximum 42.37. I always have this tiny bit of excitement and scared. I showed them if that number is completely different than the number we calculated here, that opens up a whole bunch of problems moving forward. But luckily, it worked out. So again, here, this question in grade 12 pre-calculus, only able to do if you had graphing technology. Okay? Now I'm telling you, most universities, if they allow you a calculator on your exam, don't allow you graphing calculators for obvious reasons. And so what would this mean if this was a calculator question, but I still had to solve it? We now see that we could, right? It creates a quadratic equation. We can use our quadratic formula. Quadratic formulas also, we say like you learned that in grade 11. Now this is 2 years past. Usually when formulas are learned 2 years ago, they start to become things that are just expected at that next level that you know. So the more formulas that you can remember, they are also going to help you for university as well. So you've got a right angle triangle here, and A and B and B and C, their sum is always 6. So one of the skills that we're also going to develop, besides not losing our pen, is to write things in terms of x. And this one has set it up for you. They say, let's make A B x. What would the length of BC be? If they have to add up to 6, this is going to be 6 minus x. If you're ever struggling with how to do that, use a number, right? If x is 1, what's the other side? You're like 5. Okay, take a step back. You figured that out really quickly. How did you do that? You were like, oh, I figured out what needed to be added to get to 6, or I subtracted, and then you're like, oh, it's not hard to figure out 6 minus x. Now, for most of you, the 6 minus x here is really easy and no problem, but you will get into more complicated situations where you're going to have to sort of think that way, and that's a great problem-solving strategy. Solve something simple and look at how you did it, then see if you can apply that to a more complicated situation. Then find the maximum area of a triangle, base times height divided by 2. So we plug in the values that we have here, multiplying this out. And all of our algebra skills now we start to use our algebra skills to be like, well, what's going to be nicer for me to do the derivative? I could, like with this 2 on the bottom here, I'm like, I could do that as a quotient rule, which would be kind of awkward. Or maybe I put the half out in front and think of it as a product rule. But if I do a little bit of simplification to get to this last part, then...
Mr. Terry, isn't it plus 6s?
Is it? It's x minus 6, right? Yes. Let's just...
No, it's 6 minus 1.
It's 6 minus x.
Yeah,
Okay.
within the next step.
Oh, yeah. Thank you. There we go. There we go. Yes. So you get negative x plus 3, set that equal to 0. If we had kept the 6 as the mistake that I made, we would have solved for x and got x equals negative 3. And that should have set up some red flags. Like, oh, one of the sides has to be negative 3. Right? And then, right, sometimes we should always look at our answers and be like, does this seem reasonable? Before we keep going. There used to be, on the grade 12 applied exam, there used to be a section on design and measurement where you had to design something within parameters. Like they say, you have this much space, what are you going to do? And how are you going to build it? And I used to say, what I would like for this assignment is, after you do your work, you have to go to Home Depot and load up all the materials you put down on paper onto a cart. And then bring your cart for the final examination. They say, yeah, you have everything. Because there was this one project where this person bought, like, if you ended up doing it, to build their patio in their backyard, it was like 15 semi-loads of bricks it would be. It's like, at what point when you were loading your cart, if you had to actually load your cart at Home Depot, you'd be like, I made a mistake. I've loaded 100 bricks, and I need to load 15 million more. I will have the biggest patio in the world. Oh, there was one time someone built a barbecue that was literally this big. A toothpick couldn't even fit on it, and they were designing this outdoor barbecue. So, again, when you get your answer, think about it. Does it seem reasonable? Is it within the framework? Does this make sense for our question? Yes. I get one side 3, the other side 3. This will work out. And now we can go beyond some of those questions that would still have been asked in previous years and start using this to solve more questions. This is one of my favorite optimization questions because, well, I'll talk about it afterwards. We'll solve it first, and then I'll talk about why this is like a fascinating question. So, a closed right circular cylinder, in other words, probably should have like this one. Okay. In other words, just a cylinder, but right circular means that the base is a circle instead of being something else, and right means that it goes straight up instead of having a bend. So we have all of these other types of cylinders. We want to make sure. Up until now in our language, this would just be what you would think of as a cylinder. Okay? There's a base of radius r, so we know the radius is r, and has a height of h, and a volume of 54 pi centimeters cubed. Now we could do this as a real life question with a cylinder and think about it afterwards, the volume would probably not have pi in it. It has pi in it so that our numbers work out nice as we're solving. We want to show that the total surface area of this cylinder can be written this way. So first of all, either A, you would have to know your surface area of a cylinder formula, or you'd have to look it up. Okay? Surface area of a cylinder formula is one of my favorite formulas. I have lots of favorite formulas, but it's one of my favorites because surface area, you know, is the outer stuff, right? Everything that would take part to cover or paint the whole shape. You probably would understand easily by looking at it that the surface area formula would have two circles. So it has 2 pi r squared, a circle on the top and a circle on the bottom. But it's also going to have the rounded part that goes around it. And this is why I really like this formula, is it's so nice to visualize. Here is a cylinder shape. It has a lid and stuff like that. But if there was a label, and you can think of a soup can, and this label, I like how my cylinder fits this paper almost perfectly, right? When you take the label off of a soup can, you get a rectangle. And that rectangle, first of all, I hope it's pretty obvious that the one side of the rectangle is equal to the height of your cylinder. But the other side of the rectangle is really beautiful because if you visualize it without pouring out too much water, right? If you visualize it, what is that? That's just the circumference of a circle. So circumference is 2 pi r, and that means that for our surface area formula, the area of that rectangle will just be 2 pi r times h. And I always say, if you don't believe this, go home, go into your pantry, find a can of soup, take off the label, see if it's a rectangle, right? If you're not, because I want you to be critical thinkers, okay? So critical thinkers would say, just the fact that I took paper off of this cylinder, you should be like, does it work for all cylinders, or is it just unique to this one that it makes a rectangle? Take the labels off every single can in your parents' pantry. It's another rectangle, and be amazed every time. And then choose to decide to put the labels back on, or not. And enjoy your suppers for the next 2 weeks. Now, the problem with creating the surface area formula like this is well, that's not the problem, but right now our surface area formula has 2 variables. It has an r and it has an h. So if I wanted to find the derivative of this with respect to r, I would have to use implicit differentiation because I have another variable in there. We've done implicit differentiation, but even better is if we can take this equation and have it only in terms of one variable, either only in terms of r or only in terms of h. And the key to this will be the fact that I know that my volume formula for a cylinder, okay, and I really like this formula as well. I like it because I hope you see that it's just a circle times a height. And if you think about volume as filling something up, I think it's really easy to see how this formula works. Because pi r squared would be like one piece of paper sitting at the bottom. That's just your area of your circle, one piece of paper. Now, if you kept stacking up papers on top of it, on top of it, on top of it, you would fill this whole cylinder full of paper. And each of those circles is adding up to the height. So this is just the area of the base times the height, bunch of circles piled on top of each other, would fill the whole shape. And now we're like, okay, surface area formula makes sense to me. The volume formula makes sense to me. If you have those kind of visuals that make sense to you, then in university, if they don't give you these formulas, they're that much easier to remember. Whereas if you're like, okay, I'm just going to remember these things, right? And without meaning, this would be very hard to remember. Okay, so we've got our volume formula, and we know that our volume, wow, now I've lost 2 points. We know that our volume is 54 pi. And so here, I can rearrange this to get h by itself. When I divide both sides by pi, they'll simplify, but dividing both sides by r will give me that. This allows me to rewrite this, but instead of writing h, I can substitute in 54 over r squared and multiplying this out gives me that 108 pi over r. What's nice about that formula? Only one variable. Now I can take the derivative of the surface area with respect to the radius. I can find ds dr because I'm only using 2 variables, whereas before with the r and the h, with 3 variables in that equation, I'd have to use implicit differentiation, and I would still need to do and find this equation to make that work. So this allows us to find our derivative. I'll just write it out again. Are you okay when I rewrite this again if I, instead of write it as over r, change that r to the minus 1? Again, I'm pre-thinking what's going to make my life with derivatives easier. The r on the bottom, I would have to use a quotient rule. The r to the negative 1 allows me bring that negative out in front to do this. So we want the surface area to be a minimum, set it equal to 0. Now, solving for this. Personally, I saw you guys do a bunch of different things. I kind of like getting rid of fractions in an equation if you can. Okay, so sometimes people get rid of fractions right away here. Other times I see people really like to move this 108 pi over r squared to that side. Then it's really easy when you multiply both sides by r squared. We get a cubic equation. I can get that r cubed by itself by dividing by 4 and pi. This is why the pi was there. Oh, pi's nice to cancel out. Oh, it's a 27. Do I happen to be able to do this in my head? Yes. So nice. Okay? This is a bad example because real life doesn't work this way. In real life, if you try to solve a problem given the stuff that you have, I guarantee you your numbers will not be nice. Okay? But now we know that the radius is 3 centimeters. The height, which was figured out to be 54 over 3 squared, would be 6 centimeters. And did it ask us to find Find the radius and height, which makes the surface area minimum. Didn't ask us to actually find the surface area. That's the minimum, so I'm okay with leaving that. But the reason I find this question so realistic to life is we could change this to an actual number, okay? A can of pop is basically a cylinder. A can of pop would have a volume of 355 milliliters. And 355 milliliters of water, which Coca-Cola or Pepsi is basically water, is 355 centimeters cubed. So first of all, I don't know if you've ever done this in science, 1 milliliter of water is 1 centimeters cubed, okay? Sometimes when you went to get a shot, maybe you got a COVID shot, they gave you a certain amount in an injection. And sometimes you'll hear the medical profession saying, oh, give them 10 cc's of this. I don't know if you've ever heard that language. cc stands for cubic centimeters cubed. They're basically saying give them 10 mils, but maybe cc's is easier. I don't know why, but it's the same thing. So that's an important, just real life kind of thing. So we could have solved this question by switching the 54 pi for 355, and we're now solving a can question. And we just figured out with these numbers that the radius should be 3, the height should be 6. Why would it be important to minimize the surface area? Well, the surface area costs Coca-Cola, Pepsi, whatever company does it, it costs them money because they have to pay for those materials, right? So if you can minimize the materials and still fit the same amount of liquid in there, that's going to be an advantage, right? But this is where, like, manufacturing and everything is so intriguing to me. Because Coca-Cola is like, yeah, I want to minimize. But then, here is the minimized part, but it's not structurally sound. So now we have to change some design elements. Okay, now we've designed something that's going to minimize material and is structurally sound, but we can't actually make it without a very expensive machine. So now that adds to our costs. So now we have to, like, there's so many variables in real life. Here we've used calculus just to solve minimum. That's going to be our starting point. So they have a can, right? Is the radius of the can double the height? This is the next thing I noticed. Is it just this example that it's double? Or does it minimize often and always come up with half and half proportions? Is that just a coincidence, or should that be something? If I think about a can of Coke and I think about it, yeah, it's about, it's not the best estimation to go by just thinking of holding it, but it is about double. Gatorade could have saved some plastic, probably in their shape, but then there's other things that come into effect. If they want it that big, but it doesn't fit your hand, you're like, this is a great water bottle. I'm so happy that they made this way. I've got to use 2 hands every single time I can. So another variable comes into play. And all of these things have to come together if you are trying to design something that somebody's going to buy. You can't just think about minimizing material. You can't just, you've got to take all of these variables in and make something. And then you find out, okay, this is how it's going. What can I tweak? What kind of things can I make a little bit different? And how will that change things? And so that's why I like this question so much. All right, that is end of optimization